So what I'd like to talk about today is the nuclear Overhauser effect and its application to stereochemical and structure, particularly conformation, but structure determination. So I wanted to start, this is a fantastically useful technique, particularly if you're making molecules or otherwise asking specific questions on stereochemistry. And one of the things that I've emphasized in the class is that we don't typically just have an unknown sample plopped in front of us in our research and have to answer what is it. Often you do a reaction or you have a very specific question that you're asking. You're doing a aldol reaction and you're asking, am I getting syn or anti-stereochemistry or Michael addition as we did to the nitrocyclohexene ring, or Diels-Alder reaction? You're asking, am I getting the endo product or the exo product? Or often you'll have a mixture of two products, two diastereomers, and you'll try to want to determine which is which. And we saw in certain cases, coupling constants can be incredibly useful when you know the conformation of the molecule. They can be very valuable. Nuclear Overhauser effect. So coupling constants provided information through bonds. The nuclear Overhauser effect is a through space phenomenon. So the nuclear Overhauser effect you'll hear it referred to as NOE. I think maybe we can describe this as a change in intensity of the resonance, I'll say of a proton. Could be for carbon, we've talked about it in that context as well. Upon irradiation of a nearby proton. And let me show you what I mean schematically. So let's imagine you have some molecule and you have two hydrogens in it, HA and HB. And they're not necessarily near to each other by way of bonds. They're not necessarily J-coupled. In fact, usually you'd use this for a case where they're not J-coupled. And if we irradiate HA, what we'll see is that the signal of HB is going to change in intensity. So in other words, when we irradiate HA, so let's say HA is at 2 ppm. And so we apply, and let's say we're on a 500 megahertz spectrometer. So if we apply a radiation electromagnetic signal at 5,001,000 hertz at what corresponds to 2 ppm, we're going to flip the spin of HA back and forth. So we're going to level the populations of the alpha and beta states, and that's going to alter the population of alpha and beta states of HB So irradiation of HA is going to alter the population of alpha and beta states of HB by opening new relaxation pathways. And so what that's going to do is it's going to change the intensity of the signal of HB. All right, so let's imagine for a moment that we have that situation, and let's just draw our peaks as singlets. So let's suppose we have a signal for HA and a signal for HB in the spectrum. So this is the regular spectrum. And again, in this hypothetical example, maybe HA is at 2 parts per million, and let's say HB is at 1 part per million. And let's say we're at 500 megahertz. So we're applying a 500 million 1,000 hertz signal that levels the population. And so we see that HA's peak disappears. And schematically, what I've tried to do is show that HB has gotten bigger, right? So we're radiating over here at that frequency, and the HB peak has gotten bigger. The theoretical maximum for an HHNOE is 50%. In other words, in practice, that signal could get up to 50% bigger. On the other hand, it's rare that you'll see more than 20%. So in practice, 20% would be a big NOE. Now, I gave the example for hydrogen because that's the most useful practical thing for structure and stereochemistry determination. But in every C13 NMR spectrum we're running it with proton decoupling. And I've already talked about NOEs, and I mentioned that the carbons to which hydrogen are attached are usually bigger. And you've seen that, right? The quat carbons are typically very small in the carbon NMR. The signals from them are very short. The CHs are much taller. When you look at an aromatic spectrum, when you look at the aromatic spectrum, say, of the problem 2 that we had on the midterm exam, you could immediately, even without the depth, pick out that there were 3 CH carbons and 3 quat carbons. And part of the reason for that difference is that the hydrogens are getting irradiated. You're doing a proton decoupled NMR with broadband irradiation of the hydrogens. That's making the C13s bigger. And in this case, you're getting a NOE of up to 200%. And that's in part because remember with carbon, your difference in energy is about a quarter as small because the magnetogyric ratio of carbon is about a quarter that of hydrogen. So the difference in population of alpha, beta state and beta states is very, very small for carbon, and it's only, shall we say, very small for hydrogen. And by opening the populations of alpha and beta states of the hydrogen to the carbon, you can get a bigger gain. NOEs can be positive, and this is the case with small molecules. But for large molecules, for high molecular weight, and I'll say, for example, greater than 2,000 would be typical, or to some extent with a viscous solvent, you'll have lower molecular weights. Then your NOEs can be negative. So instead of getting taller in the positive direction, your peak will actually get to be negative. And normally you'd be doing this in what's called a nosy. And there you have up to negative 100% max. So we're going to be focusing on small molecule NMR. And in small molecule NMR, I can tell you that when we're talking about close, we're usually talking about less than 4 angstroms, usually about 2.5 or maybe 3.5 angstroms to pick up an NOE. In biomolecular NMR, where the molecules are high molecular weight, i.e. proteins, RNA, DNA, and so forth, other biopolymers, the NOE signals are so big that often you can pick up distances that are even bigger, sometimes even up to 5 angstroms, or at least greater than 4 angstroms. Now, as you might imagine, if this is the case for small molecules, molecules say under 1,000 or under 800 molecular weight, and this is the case for very big molecules, so you're going from positive to negative, there's a region in between that's often 0, and that would typically, none of these are carved in stone because they all depend on the solvent viscosity, they depend on the field strength of the instrument. But a good rule of thumb is that for a molecular weight on the order of 1,000 to 1,500, you'll often get 0 NOE. Or thereabouts. And this is a problem. And there's a technique called rotating Overhauser effect, or ROEs, that allow one to overcome this, and we'll talk more about this in a little bit. I just want to show you what this means in a practical sense of how you get a typical one-dimensional NOE spectrum. And I'll show you first with a little diagram, and then we'll look at some real experiments. So the simplest NOE experiment that's often done is called a difference NOE experiment. And this is not exactly what we do right now. What we do now is usually a gradient NOE experiment, a pulse field gradient NOE experiment. But I think it's a little easier to explain and show the difference NOE experiment. So let me show you what I mean, because this is what we're going to be looking at. And indeed, this is the type of thing you'll be looking at, regardless of whether we're talking gradient NOEs or whether we're talking difference NOE. So you might have a spectrum here, and I'll give sort of HA, HB, and HC kind of diagrammatically, or the resonances thereof. And we'll have this example where we irradiate HA, And so now, as I showed before, we've leveled the population of HA. HB has gotten a little bit taller, but for contrast, HC has not. And so if we subtract, and that's why we call this a difference NOE, specifically if we take the spectrum and minus it from the irradiated spectrum, what you'll see is something that looks like this, where now the HA goes down. The difference on HB now is a small residual, and the difference on C is nothing. And you would probably slap an integral on this, like so, to measure the amount that it's gone up. And you'd see something like this. So I want to show you a real example, and this is a real example from the book Derome. Derome is a book that was written a number of years ago, and it got updated as Claridge. And I think you've already had some reading assignments from Claridge, but I've taken this handout from the older Derome book. All right, so this is your handout. And this is an example of an H1 NMR spectrum. And in this particular example, you can see there's a peak at 4 parts per million, 4.2 parts per million, singlet. There's a doublet at about 2.2 parts per million. There's what looks to be a doublet of doublets at about 1.2 parts per million. And there's a singlet at about 1.1 part per million. And so in this particular example, the authors tried to irradiate this doublet of doublets. And usually when you're doing the irradiation, it's very hard to hit just a peak without hitting anything that's close to it. In other words, to hit the peak at, say, 1.2 ppm without hitting the peak at 1.1 ppm. If the peaks are 0.2 of a ppm per million apart or more, it's easier to be selective. But these two are really close. So they irradiate this, and you'll notice because they're trying to modulate the power and not hit this peak at 1.1, they're not fully irradiating it. There's still some residual signal, but you can see it's gone down. And so here's so this is the spectrum with irradiation. And then here, this is the difference NOE spectrum. And the reason I wanted to show this to you is you can see the real sorts of issues and artifacts. So you can see that that peak, which Derome called number 3, that doublet of doublets, has indeed gone negative. What you're seeing here is the fact that it's almost impossible to be completely selective when peaks are this close. So this is the irradiated peak here. And we see a nice NOE over to this doublet here. And you can see, and this is very typical, you'll see a subtraction artifact here. where the peak has shifted a little bit. Now you'll notice that there's no net area. If I slapped an integral on this, the integral would go up and then down. There's no net area, and so there's an element of interpretation here. And the other thing that we wouldn't be certain of is we couldn't be certain, since we didn't get complete selectivity, that it wasn't that we were getting an NOE from the singlet, which we had partially irradiated. I'd be pretty sure, but what I would do next would be to do the reverse experiment where I'd irradiate this doublet and then see if the doublet of doublets gets larger. So what I want to point out then is that the NOE experiment isn't the litmus test. It's not like you dip in a strip and say, oh, it turned pink or it turned blue, it's an acid or it's a base. There is a subtle element of interpretation, and we're going to continue to emphasize this as I take us through some examples here. So this is probably a good time to stop for a moment to talk about questions.
Yeah, your last point there about the litmus test analogy. So you're saying that if you irradiate one and see the NOE with another, you want to flip it all the time, and it has to match both ways for you to confirm?
If possible. Now I tell you what, basically you want as much corroboratory data as possible. And honestly, if I had done this experiment, I might have just done the reverse experiment and said, the heck with it. I'm not going to even be able to hit that doublet of doublets selectively. The other thing you're going to see, and this will come out in the examples, is that we're going to have multiple pieces of data converge. And so in the example that I'm going to give you in just a moment, we're going to have both diastereomers, which is great because we're asking a stereochemical question. And if we only had one diastereomer in this case, we might come to the wrong conclusion. But with both diastereomers and looking at all the NOEs, a very clear picture is going to emerge. But yes, doing it both ways is good. Basically being able to check and then being able to do other resonances. So for example, I don't know what the structure of this molecule that Jerome was using was, but I might have wanted to go ahead and also not only irradiate that doublet at 2.2, but also irradiate the singlet at 4.2 and ask, okay, what happens on it? There are some other subtle things as well, in that an NOE isn't always evidence of proximity, although the strong NOEs typically are. So an interesting thing happens if, for example, you have a situation in which you have, let's say, HA and HB, and let's say HB is J coupled to HC. So HC isn't near HA, but when I irradiate HA, the population of HB changes, but you get a secondary effect over to HC that is remote. We get a small effect over here. And, you know, so again, sort of not a litmus test. If you just saw a change in HC, you might say, oh, HC must be close to HB. And yet it's not that simple. And I'll give you a quantitative example. I believe this was from a book from Jeremy Sanders, although I'm not sure right now. I didn't make a handout on it, but he's looking at this molecule here. And this is sort of similar. Remember when I was talking about determining the regiochemistry of substitution? So imagine for a moment you were trying to identify the position of this chloromethyl group on the ring. We've talked about other examples, and of course in homework in the midterm exam, in problem number 2, we had that compound with the methoxy group and the hydroxy group and the CH2 group all attached to one aromatic ring in a 1-2-4 substitution pattern. And I said, well, it's really hard to determine which regioisomer, at least among the 2 catechol that we have. So in this particular example from Sanders, I just want to give you the numbers to get a feeling. So you can see that, yes, this is an issue, but it's a small issue. So this is sort of our HA-HB-HC situation where the CH2 group is physically close to the orthohydrogen, but it's far away from the metahydrogen. And yet the metahydrogen is coupled to the orthohydrogen. So when you irradiate HA, you get a 19.2% NOE. That's pretty darn big over to the orthohydrogen. But you also get a small effect in HB. You get a negative 2.6% NOE by this type of relay effect here. So quantitatively, this is an order of magnitude smaller. In other words, it's not a huge effect, but it's something that you might notice if you do a good job and you'd wonder what's going on. And so again, this becomes, be careful in interpreting your data. Now, NOEs work by relaxation. Which means you often have to have an irradiation period that's reasonably long on the time scale of relaxation. So your irradiation needs to typically be for hundreds of milliseconds or even for seconds. So as a newbie, and we'll be talking mostly about Nosy's and gradient NOEs, where you may be doing several hundred milliseconds. For a steady state experiment, you might do a couple of seconds of irradiation. But for a newbie, when you're using the NMR spectrometer, often for the first time, and collecting a data set, and Phil has all these different parameters, and you've never done this before, and you just sort of plug in the default value because you don't know what all these parameters mean, realize that the irradiation time, or in the gradient experiments, it's called a mixing time. We'll talk more about the Nosy and the gradient NOE experiments in a moment. These matter, and they'll determine, the degree of NOE you get and so forth. Thoughts or questions?
James, I have a question. How do you specifically irradiate one proton over the other? I'm not understanding like the physical.
Oh, let's say that this proton here is at, I don't know, it'd be about 5 ppm. So let's say that this proton is at 5 ppm, and I'm on a 500 megahertz NMR spectrometer. In a typical 1D NMR spectrometer, that means I would send a signal of 500 million to 2500 hertz into my coils. That would be a radio frequency right at that. And that's what I mean by that. Same reason why when you're on an airplane, you're supposed to put your cell phone in the off mode, because you don't want the signals from your cell phone's transmitter interfering with the radio signals that are in the same range that the pilot is using. So you can probably use your Bluetooth on the airplane that's at a different wavelength, but you're not supposed to be using your cell phone that's in the gigahertz or whatever. I don't even know, maybe it's terahertz, whatever it is. You don't want to be using your cell phone that's at the same wavelength that's the pilot's one. So it's the same thing here. We're basically hitting with a relatively selective frequency. Now, in the case of the Nosy and the gradient NOE experiments, it's a little bit different than this, but from a point of conceptualization, that's what I mean. When you're doing a broadband broadband proton decoupled carbon NMR, you're irradiating those protons, all of the protons, at 500 megahertz with broadband radiation, and you're observing your carbons a mile away at 125 megahertz. And this is just a more focused example. Other questions?
That makes sense.
All right, let's take a look at a real world application. And this was a fun one. I've stolen a lot of stuff from my time in graduate school just because this was a nice chance to get sort of intimately familiar with some of these techniques. And I encourage you, once we get back into the research labs and get trained on the spectrometers, I encourage you to play around. I mean, you're sitting behind an instrument that's practically $1 million and you get to play with it. Try stuff, it's fun. All right, so here was the reaction that I was running. I was running a reaction that's called a Mccoy reaction. And I was taking an alpha chlorosylyl ketone. And the first step I did was to treat it with LDA to make the enolate. And in the second step, I added a coumarin. And the coumarin has an alpha beta unsaturated carbonyl, so it's electrophilic at the beta position. The enolate adds to the beta position. You get a new enolate. The new enolate now intramolecularly displaces the chloride. And the product of the Mccoy reaction then is the cyclopropane. Like so. And I'm going to draw squiggly lines to indicate the stereochemistry. So on the cyclopropane, of course, we have the two hydrogens on the six-membered ring, and now we have the methyl group and the silyl ketone. And I got a 3-to-1 mixture of stereoisomers. I'll say diastereomers just to be more specific. So one diastereomer in which the carbonyl is on the same side of the ring as the aromatic ring, and this carbonyl, where the silyl ketone is on the same side of the cyclopropane ring, and one diastereomer in which the methyl group is on the same side. But which is which? So let's go to the handout again, and I'll show you the spectra that are involved. So here are the two cyclopropane diastereomers. And we'll call this one isomer A, and this one isomer B. And I guess to put it another way, I've drawn the two diastereomers on top, And I've shown the two spectra, but I don't know which diastereomer is associated with which spectra. Now, which spectrum? Now let's orient ourselves, and we'll orient ourselves first in the upper spectrum, in the isomer A spectrum. Here are all our aromatic protons. Here we have our ring protons, or cyclopropane protons. Here we have our methyl group, the one that's on the cyclopropane ring. Here we have our tert-butyl group, and here we have our Me2Si. The methyls are, of course, diastereotopic, so we see two singlets. Remember, whenever you have a stereocenter in the molecule, now if you have two hydrogens connected to a carbon, or two methyl groups connected to a carbon, or two methyl groups connected to a silicon, those methyl groups are diastereotopic. And we see a somewhat different spectrum for diastereomer B. Again, we see our aromatics. We see our ring protons. We see our methyl group. It's at a somewhat different position. We see our tert-butyl group. And now, and this is really, really cool, we see our two methyls, our two diastereotopic methyls on the silicon, and they are really dispersed. One of them is at about 0.3 ppm or 0.25 ppm. The other one is at negative 0.4 ppm. So they are really there's a lot of magnetic anisotropy over there. And that's sort of cool. Okay, so the question is, which of these is which? So we take, this is a great situation because we have both diastereomers in hand, so we can do a great comparison. So first experiment. Okay, first experiment, and I guess this is technically the isomer B spectrum. So in this experiment, I picked out this methyl group and I said, okay, well, look at the methyl group. If the methyl group is on the same side of the ring as those two hydrogens, it should be pretty close to those hydrogens. So let's see if we irradiate it and if the signal gets bigger. So here's the difference NOE spectrum. And we irradiate the methyl group. And those protons, those two ring protons, do indeed get bigger. We can calculate the degree of NOE. And so on the actual printout, I measured this distance here. And I got that it's 74 millimeters. And that's 74 millimeters for 3 hydrogens. So if I wanted to calculate the integral per hydrogen, it's 24.7 millimeters per hydrogen. And I measured this integral here, and it worked out to about 2.1 millimeters for 1 hydrogen. And so if I take my quotient of 2.1 divided by 24.7, I get 0.085 or 8.5%. So that's a respectable NOE. And if I do the same here, I think I got 2.5 millimeters here. And that worked out to about 10.1%. So in other words, based on this, I'm seeing 9 and 10% NOEs. That's a reasonably good evidence that those two are cis to each other. I wouldn't say it's proof beyond a shadow of a doubt. And we're going to come back to how close is close. And I want to show you the dangers of not having multiple corroborated data. with the next diastereomer. So let's pretend for a moment that I did this reaction and I only got one diastereomer. I only got isomer A. And so here I do the same experiment. And let's say I really wanted isomer A. I really wanted my product to be that product in which the methyl group is cis to those hydrogens. And so we do the same experiment here with isomer A. We irradiate the methyl. And I look at those ring protons and I've slapped an integral on them, and you can see one here, and well, you can see the integral of the other here. And there's not much, they're very small. I think I measured them and I think this was 0.5 millimeters. And I think as best as I could, maybe, yeah, I think they were both about 0.5 millimeters. And I measured this integral here, and I think here I got it was 73 millimeters. So that's for 3 hydrogens, so it's about 24.3 millimeters per hydrogen. And I took 0.5 divided by 24.3, and I got 2%. And so when I irradiate this here, I get about a 2% NOE over to these. And if this had been my only isomer, and I really, really, really wanted that methyl group to be cis, I might have fooled myself. And the spectrum is whispering at me that something else is going on. And let me show you the little whisper that's occurring here. So look over here. You see at about 6.95, 6.97 ppm, we get a little something that gives rise to a little blip in the integral here. It works out to about 1.0 millimeters, or about 4%. So if I look at the whispers of that spectrum, that's that ortho hydrogen here. And that hydrogen, although I've drawn it far away, is on the same side as the methyl group. And so if I only had this diastereomer and I look carefully, I'd say, wait a second, I don't think it's the one where that methyl group is cis to the hydrogens. I think it's trans. But having the two sets of data together, incontrovertible, which diastereomer is which. And that's really nice when you can get multiple sets of data together. Now, let's suppose I only had isomer A, and I said, okay, I'm worried. I don't know which isomer A is. I think it's the one where the methyl group is trans to those hydrogens. I think I'm seeing an NOE to that ortho proton, but I'm not completely sure. What I could have done next is say, all right, then I better go ahead and I better do another experiment. I better try, if all I have is this diastereomer, I better try irradiating that proton and making sure. And maybe for the heck of it, maybe I should also try yet another experiment where I irradiate these methyl groups on silicon. Because if all I had was that one diastereomer, I would want multiple pieces of data helping to guide me into which stereoisomer is which. Now, with all of these questions, I could have done this either as a set of 1D NOEs, or I could do a Nosy. Nosy is a 2D NOE experiment that would give us all our NOEs at once. They're both valuable. You will get both of them in the homework. Thoughts or questions?
Quick question. When you're measuring the integral that seems to be the biggest, are you measuring it all the way down to where it stops?
Yeah, I'm measuring basically from the flat point on one side to the flat point on the other side, very much like we're doing in our 1D spectra and our regular spectra, where you're using my grid or using a ruler or using grid lines on the spectrum here, but I'm doing it downward because it's a negative peak. Other questions?
Another quick question. So on the spectrum that we just did, you looked at the ortho proton, but why didn't you look at the methyl peaks on the very right?
You mean, why did I only show you one NOE experiment? So in the one I did, oh, the methyls, okay. Let's go back to that. Good question. So, yeah, and basically I tried my best to get a look here. And it looked like this was a subtraction artifact. And it looks like, you notice we go a little bit down and up, but there's really no net change. It looks like these are subtraction artifacts. So I pretty much found every NOE that I could possibly, and this looked like an artifact. That looks like it's just another artifact. So for isomer A, the spectrum was only whispering at us. For isomer B, the spectrum was talking to us quite clearly, and putting the two together gave a very clear picture of what was going on. And then the corroborating evidence in isomer B, the first Nosy we looked at, was those two highly anisotropic methyl groups, which are being separated by the ring current of the aromatic system. So those methyl groups are having a big degree of magnetic anisotropy. All right, I want to show you a couple of sort of last points, and I want to take you to a Nosy spectrum as well, just so you've at least seen it once, and then you'll get more of them in the homework. All right, so NOE's scale, it's a dipole-dipole interaction, and dipoles have R to the -3 relationships on the strength of the dipole. And when you have two dipoles, it's an R to the -6 relationship. So as the distance between the hydrogens R to the -6. So in other words, it falls off. NOEs fall off a lot with distance. So 2.5 angstroms typically leads to a strong NOE in small molecules. But 3.5 angstroms typically leads to a much weaker NOE. And I'll give you a nice example. I'll give you, again, I think this was from the Jerome book. I'll give you this example of mesoconic acid and citroconic acid. So basically, in one isomer, the methyl group is cis to this hydrogen. In the other isomer, the methyl group is trans. And in the cis isomer, in this particular example, he gets a 29% NOE. In the trans isomer, the NOE is much smaller, it's 6%. And so again, you'll notice it's not a litmus test. It's not like, oh, we see an NOE, they must be cis. It's that the NOE depends on the proximity, just as the NOE depends on the proximity to those methyl groups. And I want to show you in the cyclopropane example. So I want to show you a couple of things on the handouts, and then I'm going to conclude just with a nosy experiment. So one of the things I did with the handouts is I just made a little table where I basically calculated 1 over r to the 6th for 2.5 angstroms, 3 angstroms, 3.5, and 4 angstroms. Right, a hydrogen has a van der Waals radius of 1.1 angstrom, which means 2 hydrogens, if they're touching, are 2.2 angstroms apart. So that's as close as you would get, except in a methylene situation where those 2 hydrogens are 1.8 angstroms apart. So I said, let's pretend we normalize 2.5 angstroms, since that's pretty darn close. And I said, okay, if we say 1 over 2.5 to the 6, 4.1 to the 10 to, times 10 to the negative third normalizes to 1, what's a 3 angstrom NOE? Well, it's about a third as big. What's a 3.5 angstrom NOE? Well, it's just about 10% or 13% as big. 4 angstroms is getting pretty small. 1.8 angstroms, those 2 diastereotopic hydrogens, is large. So that's kind of calibrating your ruler in terms of what to expect. And then the other way I like to calibrate my ruler is with molecular models. So remember, we had a cyclopropane example with a methyl group. And I just made a model. This is an old modeling program, so you do it with Pymol now. I made a model of a methyl cyclopropane, and you'll notice that the methyl cis to the hydrogens is 2.2 angstroms apart. So van der Waals contact, gigantic or at least large NOE. But trans to the hydrogens is still reasonably big, still 3.5. So again, not a litmus test. Here's kind of our citroconic and mesoconic example with the methyl group cis to a hydrogen or trans to a hydrogen on an alkene, 2.3 versus 3.7 angstroms. Here's a methyl group on a benzene ring, kind of like that problem 2, or methoxy group on a benzene ring, kind of like that problem in the exam where we're trying to place something. And again, you'll see the ortho relationship. Here's a methyl group in the equatorial position on a cyclopentane envelope. And you'll notice that the cis and trans differences aren't very big, so you really have to be careful. Here's an axial methyl on a cyclohexane ring where you're getting nice, strong 1,3 diaxial interactions. So that's a little bit of an example, but in general, you're going to want to make some models and really look at these yourself rather than relying on just a paper and pencil drawing. It's a good way to go. And I guess the last thing I'll show you is just an example of a nosy experiment. And the molecule here is a natural product called ephanamol. And the ephanamol natural product has a 7-membered ring in it that's a ketone fused to a 5-membered ring. And the 7-membered ring has a double bond in it with an alcohol group. And the 5-membered ring has an isopropyl group on it. And the isopropyl group is cis to the ring fusion, which means this hydrogen next to the isopropyl group is down. And so I want to show you the Nosy spectrum of this molecule. And this was taken from a book by Nakanishi. So he gives a lot of nice examples. And he's drawn the molecule in a realistic conformation that's borne out by the NOE data. And I just want to show you some of these NOE contexts. So your question might be, what's the stereochemistry of the ring fusion? And what's the oops, I guess I forgot a methyl group here. So this is, I believe, a CH3 group over here, not a hydrogen. And so I just want to give you a quick overview of what you're looking at in the Nosy spectrum. So in the Nosy spectrum, we see an NOE between the hydrogen that's next to the isopropyl group and the hydrogen on the double bond. It appears as a cross peak here. So that provides some evidence that that hydrogen is on the same side of the ring fusion as the alkene. We see an NOE between the hydrogen that's attached to position 4 and the methyl group. That NOE is shown over here as this cross peak. And again, as James showed you, these are really contour plots, so you can see the intensity by the size of the contours or the topography. And so that's evidence that the ring fusion is cis. And then you see a few additional NOEs that aren't as diagnostic. I mean, here we don't really have a question of stereochemistry, but we see the CH2 group next to the hydroxy group as giving an NOE to the alkene. And this is sort of cool. This tells us about conformation. We see an NOE between hydrogen 8 and hydrogen 11. And it looks like my program is trying to be too smart for itself and correcting my lines. Anyway, that NOE tells us that we sort of have this envelope-like conformation here. That's going to be relevant in your work on strychnine because we're going to be talking about your conformation of one of the medium-sized rings in strychnine, and you're going to be looking at it through NOEs and coupling constants. So this is an example of a Nosy spectrum, a lot of data in one place, even possible in a nice crowded spectrum. Both are useful, both the 1D and the 2D spectra, and I will often do both 1D gradient Nosies and 2D gradient NOEs and 2D Nosies. So we've pretty much come to the end of our time, and I'll let anybody go who needs to get going, but I'm also happy to take any final questions on today's class.
So this Nosy spectrum here, you mentioned it's like a contour plot. Will it also tell you the magnitude of the relative NOEs?
Excellent question. So one of the tools available in TopSpin or in the software that you're going to be using is called a volume integral. They're a little trickier to measure, but basically, remember, this is like a topographical map of a mountain. You can measure the volume of that mountain with a volume integral. Now, I caution you on all of these integrals, the numbers are kind of rough. Rarely, only under special circumstances where you do a series of calibrations in what's called a buildup curve, can you use NOEs like a ruler. More typically, they are either a very crude ruler, where you say, oh, these hydrogens are very close, or they're kind of close, or they're far away from each other, or relatively far away. So usually what I'm looking for are big cross peaks or big integrals is a strong NOE. Now, the problem in a 2D spectrum is that a very tall spiky peak goes up very high on the topographical map compared to a broad fat peak, but a broad fat peak may have the same volume. In other words, a big hill might have the same volume as a spiky little peak, but the spiky peak is going to show up more in the contour plot. So it's easy to fool yourself, particularly in the Nosy spectrum. So usually I have to be really careful in interpreting things. And small spiky peaks come from singlets and doublets, and broad hills come from big multiplets. So if you've got a big multiplet with a big multiplet, you're going to get a cross peak that's a broad hill that's going to be very close to the noise, even if it's kind of big. Whereas if you've got like a methyl group to, a CH doublet or a CH, triplet or something like that, you might still see a sharp spiky peak. So you have to be careful, particularly with the Nosy, which is why I kind of like 1D NOEs as well.
James, may I briefly share my screen? I opened up the cozy of strychnine just to demonstrate how the contours work.
Absolutely. And anyone who needs to run off, please feel free.
So right now I have it relatively zoomed out, and you'll notice that there's multiple contour lines for this particular correlation, and these look like, so I think my my calibration is very slightly off. I think this corresponds to this peak and this corresponds to this peak, but they're crossing with this doublet. But you'll notice this doublet of triplets is rather short in comparison. You can tell there's only the one contour line. If I start to zoom in, you'll see weaker correlations start to pop in on their own. But this already has several contour lines indicating that this is a steeper climb. So this is already a much taller peak than this is as I start to bring in the weaker correlations. Does that make sense?
Yeah, that looks good. So you're just like going down different planes from the overhead view here.
Exactly. That's exactly how it works. Yeah.
And one of our jobs when we try to make up spectra, or try to make up problems, and of course, when you try to make up your spectra and your dissertation and your research for publication, is to choose your levels wisely in order to basically come up with a representative spectrum. A lot of journals allow you to deposit the FIDs, to deposit the data set. And the only problem with that, people have said, well, why don't you just give us the FIDs for the exam? And all I could imagine would be that the final exam, which might take people 12 hours, would become a week-long affair. So we usually just provide carefully curated spectra. And I guess that's one of your jobs as operators on the strychnine spectra, is to try really to do a really careful job. As we move along with the strychnine problem, we're going to culminate with your assigning all of the resonances and analyzing your spectra. And that's going to be really, really important, because that's where you really crystallize this practical understanding of doing NMR and interpreting your own spectra and not having them pre-digested for you. All right, well, on that note, I think I will let people go. Thank you for sticking with us. Thank you for sticking with me, and I will see you on Friday.